Okay. Okay, so I assume we're live. Let me share my slides. So we have a little bit of a glitch here, and that we are missing the speaker, and we think he's on the way. It reminds me a little bit when I lived in England. I was once trying to take a train from Cambridge to London, and the train didn't leave, which was not so unusual, but it didn't leave for quite a while. At some point, they made an announcement that the driver is still missing. So we are missing the driver. So now we have an amateur driver who will try to entertain you a little bit for the next 5 or 10 minutes. And whenever Shakir shows up, I will stop and we move to his talk. So I used to teach kernel methods in machine learning summer schools. I haven't done that in quite a while, but I have one fun slide that you might enjoy. And so you had the course taught by Arthur. So you know what a positive definite kernel is. Is that correct? I think so. Huh? Yeah, I see some people nodding. So let's look at some concrete examples, and maybe some of them you've seen already, right? So let's see. So let's assume in everything below x prime are from some non-empty set x. Could be a vector space, doesn't have to be a vector space. So let's look at the first question. Is this a positive definite kernel? Can we have votes? Can people vote up and down? Okay, so please cast your votes.
Yes, they can raise hands so we can count how many. Sakir is here already.
Should we do the first quiz at least?
Okay, and then let's, well,
yes,
this one is a trivial one. Okay, this is a positive. Okay, then I'll run very super fast. This is a kernel. Next one, is this a positive definite kernel? Put your votes. Oh, it's not. Okay. What about this one? So you have some positive definite kernel, and then you multiply this function from the left and right. And it could be a function that's positive or negative. Is this a kernel?
4 people say yes, 6, 7.
It is a kernel, yes. Next one, what about this? The cosine of the angle between two vectors in a dot product space. Is that a kernel? Yes or no? You have to be super fast. We don't want to steal time from Shakir.
About 10 people.
It's a kernel because it's a special case of this thing before. I'm not going to say why, but you think about that. Okay, what about this? A maximum of 2 numbers, real numbers. Is that a kernel on the reals? It is not. What about the min of 2 numbers? Is that a kernel? Yes, it's a kernel. And you can think about a proof. There's a simple proof how to construct an explicit feature mapping from x to some function such that using a suitable dot product, you can recover the minimum of those 2. And let's skip this one. This is a kernel, yes. What about this? Is that a kernel, the delta function? It's a kernel. This is too complicated, too long. Let's see if we have some more fast ones. Is that a kernel? So you exponentiate another kernel? Yes, it's a kernel. What about if you take the logarithm of a kernel? That sounds like the opposite. Yeah, no, it's not a kernel, but it can be positive definite. So it's just not generally a positive definite. What about this K of A and B, where P is a probability measure? So the event of A intersecting B, the probability of this event, this is a positive definite kernel. What if you subtract something? Is it still a positive definite kernel if you subtract this thing here? That's a nice one. This is still a positive definite kernel. I think we have that one in our book if you're interested. What about this? Is that a positive definite kernel? I think we've seen that one before, yes. What about if we raise it to the power of 3? Is that still a positive definite kernel? No. What about if we raise it to the power of 1? That's a positive definite kernel. Okay, so let's stop here and move to Shakir. Thank you very much.
Thank you, Bernard.
I just, does it work? Sorry, everyone. I had it off by 1 hour error. I don't know why. So yeah, let's, should we just jump in and present my screen and we take it from there?
Yeah, yeah, sounds good. So yeah, this is the last lecture of the summer school. Yeah, you already know Shakir. Shakir, the floor is yours.
Thank you. I'm gonna do that. Hopefully we have this. And you can see my screen now, so that's great. What are you actually seeing? You are seeing the...
We're seeing the speaker view.
You're seeing the presenter side, all right? So I'm just going to invert these. And hopefully... let's see, what do you see now? Not now. One second. What is going on? Okay, sorry everyone, I was just presenting the wrong screen, but I think now it should work as expected. Is everything good, Georgios? If you just give me a quick...
Yes, everything is good.
All right, great. So hopefully everything is set up. So yeah, thanks everyone. And again, apologies to be a few minutes late. I don't know why I had it picked up, but we'll make up the time and everything will sort of work out hopefully as we expect. And I want to just pick up from yesterday. We went through an hour and a half where we spoke about Bayesian basics, where we looked at some introductory concepts of what it means to be Bayesian, Definiti's theorem as a basis for thinking about integrals, priors, likelihoods, and marginalization. And then we went on to the idea of Bayesian computation, where we looked at the central problem as being one of integration, and many different kinds of techniques for integration. And we looked at two approaches, one using conjugacy, which was an exact integration method, and Laplace's approximation, which was an approximate integration method. So today we're going to do a bit more advanced work on Bayesian approximations, and then at the end, some work on Bayesian futures, just some other topics that we won't have time to touch on in too much detail, but we'll just do a little bit of surface analysis on that front. So this part of Bayesian approximations, I have basically three kinds of ideas that I want you to have at the end, is to think about direct and indirect inferential methods, to then do a short exploration on Monte Carlo methods, and then in the end, to do a bit of work on variational methods. And then we'll just wrap things up. We'll take a bit of break after this segment and then move on to the next part. So yesterday, we sort of enumerated some of these kinds of inferential questions. So these were questions about how to compute integrals which come up in all sorts of Bayesian computation, whether we are computing the evidence here, which is integrating out any unobserved variables, whether they're parameters or latent variables, computing summary statistics like means or other moments of distributions, posterior distributions, and more complicated questions, whether we are integrating over a path like we would do in reinforcement learning and planning, or looking at the impact of certain actions on information gain like we would do in experimental design. And one of those components of the model inference and algorithm components that we spoke about yesterday was to think about learning principles. And I put forward to you this hierarchy of statistical inference methods, which looked at direct methods and indirect methods. And very briefly, I described direct methods as those methods which directly try to compute the marginal likelihood, P of X, or an approximation of it in some form. And we mentioned a few of them. We looked at maximum likelihood as one way yesterday and maximum a posteriori. We also looked at the Laplace approximation. And I mentioned very briefly the integrated nested Laplace approximation, which tries to improve on this method. So today what I want us to do is to focus on this direct estimation method. We're going to look at the expectation maximization algorithm. We're going to look at Markov chain Monte Carlo and variational inference. And then all the other methods sort of build up as more advanced techniques from those. Then there is this other class of methods, which I have in other kinds of lectures on indirect methods. They are ways of looking at the probability P of X, not by computing it directly, but only looking at it in relation to how it behaves with respect to some other distribution that we know. So two sample comparisons do this. You have two different distributions and you're trying to compare them. The method of moments is another one. Approximate Bayesian computation does one. And you have some transport methods, MMD. They are all methods I've put into this other category. And we won't look at those. We're going to just focus on the direct methods. So maybe the question for you all, and again, let's do it as we did yesterday. If you can just take 1 minute to think of your answer to this question. How do you represent a distribution? And there are many ways of representing it. We looked at some yesterday. So if you could just take a minute, think about this question. And hopefully, if a few of you would like to, please raise your hand in a minute or so, and then just speak out loud just to give us some ideas for what you're thinking about this question. Okay, I'm back. I got myself some water. I don't know if there was any takers on that front. If anyone wanted to raise their hand and give us a sense of what their answer to that was. I see there is one person. Okay. I don't hear anything. I think there was Tan.
Yes.
Hi, please go ahead.
Yeah, I just give my guess. So we can represent a distribution by, say, a closed form formula if we have closed form, or if we don't, we can represent by a set subsets, like approximation.
Mm-hmm. Great. I think those are two very good answers, and we looked at some of those yesterday. Closed form through conjugacy and also through approximation like the Laplace method. Was there anyone else who wanted to give some other answers? Let's see, Pierre.
Yeah, I would say like a measure from measure theory. If we got the Radon-Nikodym property, a density with respect to some reference measure. And otherwise, we can also look at it from samples as a limit distribution of some trials, for instance.
Great, thanks, Pierre. Yeah, so that's a really good point Pierre is bringing up. If you have a density, then you, or actually even if you don't have a density, and we'll bring this up a bit later on, for infinite dimensional objects like you were just studying with kernels, then it would be better to use the way of representing distributions through their measure theoretic properties, because then we can actually do much more with them. And then the very practical solution that Pierre just brought up around samples. I don't know if there was anyone else who wanted to give a go.
There are two more. It's Margaret
Please.
and Robert.
Go for it, Margaret.
I think Pierre just said mine. I was going to think about sampling from a distribution and showing histograms and things like that.
Yeah, that's great. Histograms are very important to all of us because it's sort of the first thing we learn and actually the thing that lives with us forever as a way of representing a distribution. So excellent, thank you. And one more person?
Yeah, so I think like an algorithmic perspective, maybe in a sense like Box-Mueller algorithms for sampling from a normal distribution, and I guess rejection sampling and all these ideas also related to sampling, but more, I guess, explicit or, yeah.
Great, amazing. Thank you, Robert. And that is actually the last answer of what I have on my own slide, is that there are ways of representing samples through procedures of samples, or we can think of sampling programs. So let's just go through those slides together. Thank you all for that. So we have many ways of representing distributions. We have the closed form or analytic method. So those ones would be all the distributions in the exponential family, like the beta distribution, the normal distribution that we looked at yesterday, and mechanisms of manipulating them through conjugacy and through other properties of the exponential family. Or we have methods like approximations. Yesterday, we looked at the Laplace approximation that fitted the closest Gaussian, and then because the Gaussian or the Laplace was a quadratic function, we know how to integrate quadratic functions almost always, and even integrating quadratic functions against other functions like sinusoids, etc. So both of you mentioned this. Thank you, Tran, for that one. Then the point that just got brought up by Margaret, by Cyril, around samples and histograms themselves. If you cannot represent the distribution, you can just collect the set of points together, and the set of points of where they are will be the samples. And it looks pretty good in 2D, and we'll have some trouble with this in higher dimensions, and we're going to look at why and how you have to do computation when you have a set of samples. And then the final set that I have here is around sampling procedures or programs, that there are ways of generating samples and representing distributions, not in the analytic form, but in components that when they are stitched together, give you a distribution. And some of you, just to give a bit of a jump ahead, methods like normalizing flows are ways of doing this, or other kinds of analytical processes. The Box-Mueller algorithm is one of them that looks at polar transformations. And this example here that I'm showing you is called the inverse CDF method in this particular picture. So yesterday we looked at the closed form and the approximation. Today we're going to look at samples and sampling procedures. And when we begin with samples, we need to study first go back to that question of how it is we compute integrals. And so here now enters the Monte Carlo method. And I want to take a bit of time because the Monte Carlo method is deceivingly simple, but very fundamental to almost everything we do in machine learning. And so the Monte Carlo method is one of the most general methods we have for computing integrals, sums, and probabilities. So if this is the integral problem that we have, some generic function f, it's a function of theta in this case, because I'm integrating x. I'm going to take f times the f of x, and this notation that I used was always expectation under some distribution p of the function f. And the Monte Carlo method is very simple. It says, if you want to compute this integral, what you will do is break it up into a sum instead, where you will first draw samples from the distribution p, then evaluate those samples on f, and then compute the average. So now the language that we would use here is we would say after you do create this sum, we call this object an estimator of this integral. And so estimators are the objects that we are typically going to study, and we're going to look at the properties of Monte Carlo estimators. Now, what's important to just keep in mind about the integral problem that I'm showing here is that almost everything we do in machine learning, all the tricks of manipulating probabilities that we are using, are going to try and rewrite the integral in this form, in the form of some function that we want, and a distribution that we can sample from. And if we find we have an integral that is not in this form, a distribution that we can sample from, and something we want to evaluate so we can compute the average, we are going to use every trick we have available from mathematics, algebra, geometry, measure theory, etc., differential geometry, to change the integral into a form that has that mechanism. And I think if you just realize that, then many other more advanced methods, particularly ways of computing gradients, become much more obvious, because all the tools of computing gradients try to rewrite it in this form. So I'm going to move on from there. Some interesting properties of Monte Carlo methods that we are always trying to look at, there are 4 of them. One of them is called consistency. So when we typically, Monte Carlo methods are always consistent. That means if you compute this problem, on average, it will converge to the true integral, especially as you're taking n to infinity. So consistency is usually something you don't need to worry about because of the properties of the law of large numbers. So this one is usually one we can take for granted in some sense. Though if you were doing more complicated chains of things, like a Markov chain that we're going to see in the next section, then you would have to do a little bit more work on this front. Unbiasedness is usually the one that many people are interested in machine learning. So this sum that you see here, this value f of theta, is itself a random variable. And the reason it is a random variable is because you have to sample capital N different what we'll call variates xn. But you can generate many different sets of capital N variates xn just by the way you are sampling. So you can see you can generate k sets of n variables, and you could get k different answers for f. So if you take the average of that set, you want then on average to be centered around the true value, and that's what unbiasedness means. So most of our work in machine learning, we will prefer unbiased estimators, although having a biased estimator is not the end of the world. But if you do have a biased estimator, then you have to do a lot more work to control the bias. And what you want to do in those settings is to make sure that the bias is sort of decaying as you are doing more learning, or is disappearing in some sense. And I can send a paper on tricks and manipulations for handling biased methods. We want them to usually be low variance. As I said, if this is a random variable, you can compute an average and a variance just by creating multiple sets, capital N sets of these variates xn. You'd usually prefer the one that has the lowest average, because that one has impacts on the way we are doing approximate computation, the kind of variance of the gradient estimators that we're going to use if there are gradients involved, or it's about the accuracy of the method itself, depending again on how this number will be used for decision making. And of course, we're also interested in computation. We don't want to have methods of this sampling that are very expensive that we cannot actually do. And we want to be able to evaluate f, or even sometimes we can't evaluate f, we just need ways of computing these sums. So they should be parallelizable, easy to generate, require very few samples needed to estimate unbiased and low variance estimate. So these are typically 4 questions you will ask about any Monte Carlo estimator. You can ask these 4 questions of stochastic gradient descent because it is a Monte Carlo method. You can ask these questions of Markov chain Monte Carlo methods that we're going to look at. You can ask them of variational methods as well that we use most today. So this is a good starting point. I want to now look at some both methods for evaluating integrals that pick up from this idea of Monte Carlo. So typically, if this is our integral problem, let's assume P of x is something that you cannot easily sample from. In that case, what would be desirable is to transform this expectation under the distribution P of x, which may be something we don't know how to sample from, but maybe can only evaluate, into a different kind of integral where that's an expectation under something we do know how to sample, and maybe we can just modify the function and evaluate that differently. So this is basically one of the core tricks of all of manipulating probabilities and in proof theory, in learning theory as well. You're going to try and do this trick because if you know the properties of Q, you can do many other things. So how you will typically do that is by introducing a probabilistic 1. So I sometimes call this an identity trick. You can just add a 1 almost anywhere, and you can create a 1 of any distribution that you like or know or prefer to use. So let's use that to develop the first of these Monte Carlo methods that we call importance sampling. So if this is the integral problem, I want to compute this quantity m, let's call it some sufficient statistics, which is an average over this function f under the distribution P of z. Now, let's assume z is some complicated distribution. I can't sample from it, but maybe I can only evaluate it. What I'll do is then do exactly as I said in the previous slide, introduce this probabilistic 1. So multiply and divide by some other distribution, and I'm going to call that distribution Q. This may be a distribution that I know and can sample. It has some kind of good properties in relation to computing averages. So that's the one. So what I'm going to do is just reweight them. I'm going to put P divided by Q together in some new term, and I'm going to do F. And then that, there's some now conditions which comes up. If I'm dividing by something, then I usually have to be very careful. I need to make sure that Q of Z is greater than 0. I don't want to divide by 0 because that will be numerically a mess, but also just wrong because it's going to blow up to infinity. And Q of Z needs to be something I can easily manipulate. It must be something cheap and easy to do. But if I can do that, then this integral will be valid and will be the same as the original integral. And then the expectation is a new kind of expectation. I'm going to do this expectation under the distribution Q of some new evaluation function f times this ratio of P divided by Q. And this kind of ratio that comes from importance sampling is very important. We're going to go one direction of taking importance sampling in a few slides to develop variational inference. And if we had a third lecture, we would take this route of importance sampling of this ratio P divided by Q and then develop instead methods like you see in GANs or two-sample testing to do methods. So I'll just leave that for you. I can point to some other lectures and slides that I have on that topic. So this is the problem that we have. I'm just going to call that ratio W, and typically we'll call that ratio the importance weight in importance sampling. And I want to represent variance Z of S as samples from Q. And again, Q is something I can do. And so then a Monte Carlo estimator will, because I know how to sample from Q, can compute the average of this reweighted function F. And I think that's important. The importance sampling is intuitive because it says I have my original function, I reweight them according to its importance, and then I compute the average, and the importance is related to this distribution Q. So you can see if Q is deciding this weight W, if you can see what's in this picture at the back, you want Qs that typically cover all the mass of the real distribution P that you're thinking about. And if you can do that, then you will actually get an efficient kind of estimation mechanism. And I'm just writing the log form because the log form will be typically what we're going to be interested in. We're going to want to compute log probabilities, not necessarily probabilities. And that will just be the log of this sum minus log S here. So this trick of introducing an identity is very important to importance sampling. Later on, I have a slide on computing stochastic gradients, and it's very important there. If you are computing certain kinds of probability bounds, then this trick will also appear there. And if you are doing reinforcement learning, and I don't know if Doina managed to cover this, you'll have this idea of doing policy corrections or off-policy corrections, and how you can think of off-policy corrections is in exactly the same logic we use by introducing this one and then looking at importance ratios. So it's a really fundamental trick. If ever you are manipulating probabilities, you don't know what to do, just try and introduce a one and see what's possible. So the problem of importance sampling is that it is principally a method of computing an integral. It doesn't give you a way of representing a distribution that we mentioned in the beginning. It doesn't give you a way of creating samples. You get samples and weights, which are not the same thing as exact samples from a distribution. So you want something that actually gives you real samples from the distribution. So this is where Markov chain Monte Carlo enters. And it's not a complicated thing. What you should just think of when you see a Markov chain Monte Carlo or MCMC, it's just a way of creating a search process so that you can go from some arbitrary random starting point to get to a point where you can actually sample from a distribution and get exact samples from a distribution. And we're going to call the distribution that we care about the stationary distribution. And so to do this idea of a Markov chain, we need a Monte Carlo. We need to introduce, of course, a Markov chain. And the Markov chain, you have seen this maybe in several of your lectures before, creates a dependency. It says that x at time t, if x is some variable, depends on the history of all possible x's that have come before, only on the very last one. So the probability of x given x and all t before is equal to the probability of x given only t minus 1. And this is particularly useful for creating a sampling method, because we can create a search procedure by starting with some value and generating a new value starting on the one before. And we can iterate this many times and try and do this kind of random search process that probability is going to give until we can get to the stationary distribution. So the stationary distribution comes into this idea as what is being called pi here. So x and y are two random variables that are actually living in the same space of values. So pi x and pi y is the stationary distribution. I'm just introducing this idea to introduce this idea of Q. Q is what we'll call a transition distribution or a proposal distribution. And what we want, if we want to create a search method and a random search method, is to make sure that you can go back and forth very easily. If I start from y and I go to x, I can also go from x to y, and those probabilities are reversible in some sense. And this reversibility is going to be useful because it's going to help us set up a Markov chain that has several properties. One of them is what is going to be called irreducible. It's just going to mean that as I'm searching through a space, I don't get stuck in some point x. Because if you get stuck in an x, you can't do the random search. So that's what we want there. The second point we'll do is allow us to be aperiodic, which means we aren't going to create a loop between states. I'm not going to go from state x1 to x2 to x3 and then come back again to x1, x2, x3 and do this infinitely. That would not be a good searching mechanism, because then I actually want to explore the space and actually find this stationary distribution pi that I'm interested in. And these two conditions of irreducible, which means I don't get stuck, and aperiodic, which means I'm not stuck in loops, creates what is called technically an ergodic chain. And you would have to do some proof to show the ergodicity. But if you can show irreducibility and aperiodicity, then you get ergodicity. So, so this is the picture that we have there. It just says that I have this kind of looping mechanism, and I'm going to start somewhere random, and then I'm just going to go search, 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 create these transitions until I can find a distribution and I can sample from this distribution here. So this is roughly the idea that we have. I think I'm just going to switch my camera because I see that it's not using the camera that I'm expecting it to be using. Don't know why. Anyway, I'm going to adjust this then. Okay, let's go back in here. Okay, so that was these properties of Markov chains. I'm not going to say much more than that, but if you have these two properties, we can immediately, just by looking at it, create a very simple algorithm for sampling from a distribution, which will be called the Metropolis-Hastings algorithm. And it's, again, you can think of this like a way of creating a randomized search process through a space of probabilities. So I'm going to be interested in a target distribution, P of x, and I'm going to use an unnormalized form here, which is going to be P of x tilde given ZP. And I'm going to introduce a proposal. So I'm going to sample proposal values y from some proposal distribution q. So I can start from some value x and get a y. And then the Metropolis criterion is going to say compute this P of x divide by P of y, some ratio based on the ratio of the proposals with its reversibility. And then I'm going to sample a random variable. If that random variable from a uniform distribution, and if alpha is greater than that value, then I will accept it, which means I'm going to set xt plus 1 to be equal to the value that I propose. And if I don't exceed that random threshold from the uniform, I'm going to reject the method. So this is basically the basis of many Markov chain Monte Carlo algorithms. It's really a powerful method. It's very simple. It's easy to implement because it works both for normalized and unnormalized distributions. We have lots of flexibility of introducing these kind of transition distributions. They can just be a Gaussian, for example. And based on the Metropolis method, we can create almost every other Monte Carlo method. So Monte Carlo methods then There are many, many others. Someone mentioned rejection sampling. I just showed you the Metropolis Hastings, and some of you would have known of Gibbs sampling. Then you have slice sampling, which is very popular, and then many, many other variants. Hamiltonian Monte Carlo is extremely popular. And then you have other non-Markovian methods as well of sampling these ways. So there are several limitations of Monte Carlo methods. MCMC, because of this random search, because you have to sample iteratively, because you have to wait until you get to the point where you are sampling from that target distribution, they can be slow and computationally intensive. It can also be very difficult to evaluate whether the set of samples you have is actually a good set of samples. And that's something that we'll have to think about as well. And evaluating Markov chains is a difficult problem. And there is a difficulty because we are using this Markov property. In some sense, it doesn't efficiently use knowledge that we have of the samples. It doesn't use knowledge of the fact that we have come from certain places and try to spread the way that we are searching through our space. And also in the end, as I said, like all Monte Carlo methods, they are the opposite of the whole of this lecture. They eventually say to solve a Bayesian problem, you should take a frequentist approach by computing a large sample average and looking at the large sample behavior of a distribution. So there are some concerns many people have, and lots of work has been done to fix that. So you can go beyond this Monte Carlo. And one of the methods that goes beyond this kind of Monte Carlo that I looked at is quasi-Monte Carlo method. So on the left-hand side for me, you have what is the standard Monte Carlo, which just does a random sampling across space. But on the right side, you have what are called a low discrepancy sequence. These are sequences that are not random or pseudo-random. They actually have a structure, and there are many ways of developing such a structure, like lattices, for example. And these methods then, instead of just being completely independent, they actually use the fact that there is a geometry of the samples, that they have a location in space, and that you can spread the locations in many different ways. And so there's lots of fun work, I think, to do in quasi-Monte Carlo methods. Very few in machine learning, because when you look at the results, they aren't that good yet, but I still think there's lots of opportunity for quasi-Monte Carlo methods. And then a lot of the work that many people are looking at is, well, can you actually be Bayesian about Monte Carlo? And this is a really famous paper. I love reading it and sharing it with people. It says Monte Carlo is fundamentally unsound. And it's fundamentally unsound for the reason that we said in the quasi-Monte Carlo, it doesn't use knowledge of where we have come from in the past. And so what you can do instead is try to be Bayesian about computing integrals. So if an integral itself is a value that you don't know, then the Bayesian approach will say, well, what you should do is add a prior over that unknown integral. And there's a lot of work to do, and we'll look at that in the second half. So I just want to take a brief pause just to look at this picture. Yesterday, when I mentioned ideas of the marginal likelihood, I mentioned BIC and AIC as large sample approximations. They look in the limit of large amounts of data, how to compute deterministic approximations, and the Laplace approximation was there. And now I just introduced another class of methods, which are stochastic methods for computing integrals, which are based on Markov chains and Markov chain Monte Carlo. And we also looked at importance sampling as well. So I want to just look at the third part of this space. And there are perhaps other ways of looking at this triangle, but I think this is one useful way. So I want to now look at deterministic methods for computing integrals. And we're going to look at one particular method, which is variational inference and stochastic variational inference. But there are other methods in this class that we can study and talk about later. So variational methods are a very simple concept, and they're very general. A variational method is any method that lets you approximate an unknown distribution by a distribution within a known class of distributions. So in this picture, I have a class of distributions. Let's say they are a Gaussian family of distributions. I want to find, in the space of all possible Gaussian distributions that I've parameterized, the best and closest Gaussian to the true distribution that I have. And so this idea of a variational method is very general, which is why you have many, many different kinds of variational methods. But I'm going to talk about one kind of variational method, which will sometimes be called this evidence lower bound variational method, or KL variational methods. And so, as I said, one of the things that is good about variational methods is they will give deterministic approximation procedures rather than stochastic procedures that we looked at in Markov chain Monte Carlo. And the language that we're going to use here is that this approximation class is going to have some parameters phi, and I'm going to try and fit these variational parameters phi. So a brief interlude into models. Since we haven't spoken much about models, I wanted to talk about latent variable models. They are, for me, a really fun class of models to study because you can do a lot with them. They expose many difficult questions of Bayesian analysis, but also of statistical estimation as well. So a latent variable model in general introduces an unobserved local random variable that represents some form of hidden causes, whether it's phenomenological or mechanistic. So a local random variable, and I tried to explain this yesterday, says that if I have a data point xn, corresponding to that data point, I have an equivalent latent variable zn. So when the number of latent variables grow with the data set size, whereas global variables, which are parameters of a model, for example, they are fixed typically with respect to the size of a data set. And so that's the difference. And you have two types of latent variable models. You have what I call prescribed latent variable models. These are latent variable models of the type we have looked at. They introduce a likelihood function or an observer model that has some form of noise in the way you generate the data itself. But you don't need to use that. You can have implicit probabilistic models. They will also have a likelihood, but it's a different kind of likelihood, a likelihood that is implicitly defined. And they have many classes. We also sometimes call these models likelihood-free models or simulation-based models. And again, I'm going to focus on the prescribed models rather than the implicit models. And typically, inference for implicit models are those indirect methods that I mentioned at the beginning. So this is a little bit of what some real-world posteriors look like in a latent variable model of the one I just showed you in the previous slide. So these are some posterior distributions for a very simple latent variable model. It has a Gaussian latent variable. It inside has a very simple MLP, a two-layer MLP, and then has a Gaussian likelihood at the end. And these are posteriors for particular MNIST digits. And I just wanted to show you as you look at, so these are the distributions. What you want to look at is the gray images in these pictures. They are posterior distributions for these latent variables Z corresponding to different kinds of images. 2s, 5s, and 8s are what is in this picture. And I just want to show you the variety of posteriors. Some of them, like this gray one, looks very Gaussian, and you could very well model this with a Gaussian posterior distribution if you were to approximate it. Some of them look like this. They have very heavy tails. A Gaussian could do it, but typically Gaussians don't have such heavy tails, so there'll be some problem here. This one has a bit of a blobbiness. Maybe you could do it with a Gaussian or some other forms of distributions. This distribution here, because there was a switch between this one here uses a tan H as an activation function, and this image uses a ReLU as an activation function. The nature of the posterior changes quite a bit. Here you can see there's this kind of sharp dip from a high density to a low density, and here there's a very big sharp cliff. There's nothing on this side and a very long tail on this side. So what we're going to need to do is in those class of variational methods, those posteriors that we have, we're going to need to find ways of representing distributions and classes of distributions that can cover these kinds of complexities of distributions that are so varied and complex in many different ways. And that is going to be one of the key problems of these variational methods. I want to come back to importance sampling. This was the slide we went through. I said we have an integral problem, which is looking at computing this averaged or marginalized integral P of x. What you can do is introduce by probabilistic 1, a division of q divided by q. You can reweight this integral to introduce the importance weight of p divided by q, and then you can create a Monte Carlo estimator which samples from q of z and then uses the weight and evaluates the function. And then the log probability here is just simply the log of this estimator. Now, one of the important insights we get from importance sampling is that importance sampling, if you were to take the average of this log p of x over the distribution q, that is going to give you a bound in expectation of this marginal likelihood. And so how are you going to see that is we're going to need to look at Jensen's inequality. So Jensen's inequality is a trick that lets you interchange logs and integrals. So if I have log of an integral, Jensen's inequality says that I can bound that by the integral of a log of a function. And so this is going to be interesting. So this, in the second line, let's go in the reverse direction. I have an integral, like here, an expectation. This is an expectation of under p of log g. So here I have an expectation under q of log of something. I can undo Jensen's inequality and then show that this average will be a bound on the log p. And in this picture, so this was, I don't even remember what the function was. There's a joint density between p of x and z. And you want this marginal density p of x, so just looking at the one dimension. And as you increase the number of samples in importance sampling, you get a better and better estimate of the true density of this estimated. Now, one of the problems of importance sampling, as I said to you, it is only a way of evaluating the integral, so you can know the value of the density. And then you have these kind of samples that need to be reweighted, which is quite great. And you actually need a lot of samples. You can see for the tightest bound, there's something like 5,000 importance samples here. But we can take this idea of this property of importance sampling to then change the way we derive the importance sampling. So I hope you have some pen and paper. I have lots of these kinds of derivations for us to go through together. If you write it with me, you'll be able to follow very easily, and hopefully it will stick with you, the manipulation. So again, the same integral problem. It's the integral of p of x given z times p of z, and I want to be able to compute this integral in some way, or manipulate this in a deterministic way using a variational approach instead now. So I'll do the same trick. I'll introduce a 1, so multiply and divide by q. And instead of what I did now at this point in importance sampling was to introduce the Monte Carlo method. Instead, what we're going to do, so again, there's the importance weight. Instead of using the Monte Carlo method so that you'd get a Monte Carlo estimator, I'm going to apply Jensen's inequality to the log of this quantity. And so Jensen's inequality is then going to let me take the log inside the integral, and it's going to become an average over q of z times the log of this quantity. And so this then is a very different kind of quantity. I can actually split this in two because of the way of the log works. So I'm going to get an integral or an expectation under q of the log likelihood minus an integral, an expectation under q of a log ratio. And this is then basically what we call very famously the variational lower bound. Sometimes we call it the variational free energy. And it is the difference between the expected log likelihood under your proposal, and in this case, we will change the language and call this Q the variational distribution minus the KL between your variational distribution, your proposal, and the prior. So I think this is pretty good. I want to just spend some time and have us understand and interrogate what this thing means. So as I said, the language of the terms here, we introduce this Q. Q now as a variational distribution is also an approximate posterior distribution. So what it's going to do is if we do a good Q, it will help us learn the posterior of Z given X. And I'm writing Q of Z here, but it's actually Z given X. And we can call this first term a reconstruction term because it says if I sample Z from the posterior and I generate X, how good is my generated X to the real X? And then I have a penalty function, that kind of property of Occam's razor that I wanted everywhere, which says the KL distribution is a measure of distance between or divergence between distributions. And it says the posterior distribution that I have should be close to the prior distribution that I initially thought of. And this is a way of smoothing, of regularizing, and making sure you don't overfit. So this variational bound is pretty nice because it turns what was this integration problem, and if we were doing importance sampling, a stochastic Markov chain Monte Carlo problem, into an optimization problem. We can simply optimize for the parameters that are living in Q. And that's pretty nice because we know a lot about optimization. I mentioned that I'm simplifying the notation, but it's actually QZ given X. And unlike in Monte Carlo, that is very difficult to evaluate here, I can do very easy convergence assessment. And we're going to call these parameters of this distribution variational parameters. So if it's a Gaussian, the variational parameters are mean and variance. So here's a simple latent variable model. It's a probabilistic model with a latent variable y, which is a Gaussian, and a likelihood, which is p of y, and it's using some function f. This function f can be an MLP, let's say, or convolutional neural network if we're building a generative model. I'm going to make what is called a mean field approximation, which means I'm going to assume that my family of approximating distributions Q is the product of independent Gaussian distributions. And that's typically what mean field means. Mean field is about this independence assumption. I'm going to write out the variational bound, which will just be an expectation of a log likelihood minus a KL between the posterior Q and the prior. And if I just write it out, because of this assumption of the mean field, the KL will split into a sum over individual latent variables Zi. And then you can write it out. And if you actually were to compute the KL distribution between a Gaussian of this form with mean and sigma and a 0-1 Gaussian, you'll be able to prove this. So you can do this exercise later for yourself. It's a nice computation to do. And then you have this variational optimization. Yeah.
Sorry to interrupt. We have a question. I don't know if you want to take it now or at the end.
We can take it now.
So we have a question. Can we use a Gaussian mixture as the Q of C?
Mm-hmm. The answer will be yes. And just wait 2 slides or so, and then I'll speak to this point a bit more directly.
And I think we have another question from before, which is, could you please comment on the connection to optimization? I think this is referring to the MCMC. So I mean stochastic gradient MCMC methods and variants.
Mm-hmm. So yeah, let me jump quickly to that slide, or a slide which is maybe useful here. So stochastic gradient MCMC. So the core question now of Markov chain Monte Carlo, if you're going to buy this idea that it's a method of doing a search through a space, is then how is it that you create an operator that helps you efficiently search through the space? So it's basically around this idea of the proposal distribution. So methods like stochastic gradient MCMC, there's 2 ideas here. One of them is that you can use gradients of this unnormalized distribution as a way of giving you very important search operations and search directions. The other approach that those methods do is that it is what's basically hidden in this metropolis criteria. To evaluate this important sample, you have to evaluate this on your entire data set. If your data set is 100 data points, that's fine. If it's 1,000 data points, that's fine. If it's 10,000, it's also fine. If it's 1,000,000 data points or more, then this thing becomes impossible to compute. So stochastic gradient methods then try to find approximate ways of computing this metropolis criterion in an efficient way. And then you're going to have to do a lot of things, and they actually do a third thing as well in other methods, which you'll see, which is called Mala, which is that you don't want to compute this, you don't want to do accept, reject, you want to just evaluate directly. So that's basically what's going on in those methods. There are ways of getting better proposal distributions and ways of handling very large data sets for Monte Carlo and having Monte Carlo scale to larger data sets. Okay. Should I carry on?
Sorry, we have one last question, if you want to take that one as well.
Go for it.
Last question is, when is the elbow tight?
When is the elbow tight? Okay, so that's what we're going to talk about right now. So the question of the tightness of the elbow. So the elbow is tight when Q is equal to the true posterior, P of Z given X. And how you will see that is if you were to replace P of Z given X in here as Q, then you can take the functional derivative and you'll see this thing. Okay, the easier way is to take this function or this functional f, take the functional derivative with respect to Q and set it to 0 and find what is the optimal Q. And you'll see the answer is going to be exp to log px given z times P of z, which is then effectively the posterior. So the elbow is only tight and will be exactly correct and will be the true marginal likelihood when Q of Z is equal to the true posterior distribution, which is, again, this question of where these spaces of samples come in. So there are many ways of doing this optimization to help us find the tightest bound and the best Q that's possible. There's several algorithms: the variational EM algorithm, stochastic variational inference, you have doubly stochastic methods, there's amortized methods. And somehow I'm going to try and go through all of these, although our time is running out and I've severely overestimated the slides for today. So let's see. The classical inference approach says that to do this is an EM algorithm. And I don't know if you saw the EM algorithm this week, but it's always good to come back to the core question. So the EM algorithm says that I have a joint probability and I have some posterior distribution that I'm trying to compute. What you're going to do is first compute the expectation. And after you have the expectation, you can compute an M step, which is the gradient with respect to the parameters that you actually want to optimize, these model parameters. So in the classical EM algorithm, so this is how we all coded up an EM algorithm. You write a for loop for I equals 1 to the number of data points. Well, you do first a loop over iterations. Then you compute the E step, which is going to compute the gradient with respect to the variational parameters. And then you do an M step, which is a gradient with respect to the model parameters. And then you iterate these two things. And basically, the property of EM algorithms and of bounds like this on the marginal likelihood is that every step you take, you are guaranteed that you are actually tightening the bound. You are making movements in directions that your approximation Q is getting better and better up until the point where you cannot get any better, because that's the best you can do within the family of approximations Q that you have done. So that's good, but the limitation of the EM algorithm is that you won't know how to compute this expectation in closed form. So that's why for many classical methods in EM algorithm, for the Kalman filter, for example, you know how to do this in closed form. In mixture models, you know how to do this for any particular mixture, for a Gaussian mixture, for example. And what we would do in the classical or older methods, we would try to break this integral into a series of sub-integrals that we can compute in closed form. So today we don't do it this way anymore, just because we want to have far richer nonlinear functions which we can't compute and we don't have approximation methods. So just to come to that earlier question of can you use a mixture model, that is asking a bigger question of what are the kinds of families of posterior approximations that you can use. In one sense, if you just look at the bottom, there is a spectrum. There's the most expressive version, which is the true posterior distribution, which is when the bound will be tight. This you can never get to. If you knew the true posterior, you would just use it directly. So we need to look at some other things that help us get to there. On the other end, you have the least expressive, which is the mean field, which just says there's an independent set of individual distributions. But within that space, you have many other methods in between. You can use normalizing flows, which is some work we did a few years ago, which help you build richer distributions. I mentioned the idea of the Markov chain and autoregressive models. They are a really powerful way of creating other methods, which dependencies. Mixture models can certainly be used. They are a little bit more difficult to do. You can create richer covariance models in Gaussians that have more structure, and you can use what are called auxiliary variable models. And I can point you to some papers for all of those as well. So I'm not going to spend any more time on families of posterior approximations because I wanted us to do one more trick of derivation together. I wanted us to look at the methods for stochastic inference. So as I said, in the classical EM, we would first compute the integral and then the gradient. In the way we do things today in 2020, 2016, 2017, we would try to invert these two steps. We try to first do the gradient before doing this kind of integral. And so what does this mean precisely? So how you're going to do that is compute the gradient of the expectation of the function rather than compute the expectation first and then do the gradient. So this is the problem. Gradient, so now I'm going to give you a more general problem. It's gradient of an integral of some distribution q times some evaluation function f. In variational inference, this function f is the log probability minus the log prior. So there are two ways you can try to solve this gradient. Because there are only two terms in this integral, you can try and manipulate the function f, and these which we will call pathwise methods, or you can do try and manipulate the function q, in which case we're going to call these measure-based methods or gradients of measure. And in a more theoretical framework, you can understand this gradient. We would call q as the measure and f as the cost. So as I mentioned, there are two types of ways of doing this. The pathwise methods will say that I'm going to try and push the parameters phi into the function f, and then compute the gradient. And many of you may be familiar with this, which is what people call the reparameterization trick. I'm not going to spend time on deriving this one. I'm going to spend time looking at a different estimator, which is called the score function estimator. And it's going to say that I can compute the gradient of this thing by computing samples under Q and then evaluating f times grad log Q. And we're going to try and derive this second one together. There's actually a third class of these estimators as well that manipulates Q using its measure theoretic properties. So this trick is called the log.
Shakir?
Yeah.
Excuse me. So we have one more question. So in general, do you want me to keep asking questions as they come up, or shall we wait?
How much time do we have left?
So I think it's supposed to end at 3:30. I think we have a little bit of slack. I don't know, Georgios, what do you say?
Yes, we can go a bit over time, like 10, 15 minutes. Like it's fine.
Okay.
We can finish the lecture.
Yeah, so let's take the question and then we'll move on.
Okay. So the question is, are there specific ways of choosing the variational distributions?
Typically, no. This is sort of part of where the model evaluation question comes in, and you can do many other testing mechanisms. And the reason I think comes back to a bigger problem that we have in general around what it means to evaluate probabilistic models. The likelihood is one way of evaluating the model, or the bound itself is a way of evaluating, but you may be using it for other things, representation learning. You may be using it as a transition model in model-based reinforcement learning. You may be using it as an exploration function in active learning. So then the kind of distributions and what kind of error you are allowed is kind of difficult. But much of the work that we've been trying to do over the last few years was to try and find richer and richer methods that if you train them, they have the ability to become closer to the true posterior. So finding ways of parameterizing models so that they become richer. So normalizing flows is one of those ideas where we could just keep iterating on functions and use those functions to basically create richer variables. And auxiliary variable methods also try and do that as well. So in general, there isn't one best way or silver bullet way, but we are trying increasingly to find new methods that allow you to build richer and richer kind of universal distributions in some sense. And if you could do that, then you could actually push all the way to this most expressive side, in which case that's the kind of, so you typically want those distributions that are closer to this side of the spectrum. Okay, so we were doing a quick derivation. I'm going to do it a bit faster so we can actually do the second half as well. But this is a fun trick. It is basing on the trick that when you see logarithms and gradients of logarithms, you can just use their expansion to manipulate probabilities. So the gradient of a log probability is the gradient of the probability divided by the probability itself. And I think, please do this later on. This gradient of a log probability we'll call a score function in statistics. And the score function has several properties. And the one that's very useful, especially in this setting, is that the expectation of the score is 0. Now, I wish we had more time so that we could actually derive this together and so that you could actually scribble it out. But the answer or the way of deriving it is here. It's very simple. You're going to just expand this gradient of the log with this trick by replacing by grad q divided by q. You'll see that q and q are going to cancel. And then you can basically interchange the gradient and the integral. And because this is a distribution, it will integrate to 1. And the gradient of a constant is 0. And so that's basically what you can do here. And then we saw this earlier yesterday when we were thinking about information geometry. We were talking about invariant map estimation. We also came across this idea of the Fisher information, and the variance of the score is the Fisher information. And so you can see it has a very fundamental property, both related to statistical variance, which is what we're looking at here. But yesterday when we spoke about it, we thought about curvature and invariance to reparameterization. So lots of fun properties to think about of score functions, and which is why the score function is basically one of the most fundamental concepts in machine learning and in statistics, because it is the score function which is the basis of maximum likelihood estimation. So the score function gradient, let's derive it together. If you have some paper, let's scribble this together. We'll go through it a bit slowly. This is the integral problem, which says the gradient of an expectation of a function under some distribution Q, and let's take the gradient with respect to phi. I'm just going to expand the integral, the expectation notation as an integral. So it's the gradient of an integral of Q times F. So what I'm going to apply here is the Leibniz integral rule, and the Leibniz integral rule is the rule that we're going to use to say why we can exchange the gradient and the integral. And I'm going to use this score function, as we just looked at from the score, is going to manipulate Q. So I'm going to exchange the gradient in the integral and get this grad Q f of z, and I'm going to use the identity trick as well to introduce a 1, which is Q divided by Q. Now, what we can do here, and you can see the trick already, is grad Q divided by Q enters. So what you're going to do is replace that with grad log Q times f of z times Q of z. So now, basically, this is again an integral. And maybe let me just say this again, what I said in the beginning. When I introduced Monte Carlo, I said, you're going to do every trick you can to rewrite the integral that you want in a form of a distribution you can sample times some function you can evaluate. And that's what we were trying to do here. After you took the gradient inside, no longer did you have that property where you had a distribution you could sample from and something you could evaluate. So the reason that I'm introducing this identity, the reason we are using the log derivative trick is to again get to this line, which is the form of the Monte Carlo that we need. It is a distribution we know how to sample from times a function we can evaluate. And in this case, it's the product of grad log Q times f of z. And this is a question I've received many summer schools in a row, and I hope I was able to at least explain this point, a little bit of why it is we are doing this trick and trying to compute the gradient in this way. And so then you basically get in the notation that we have expectation under Q of some new function. And because of the property that I just said, that the score function is 0 in expectation, I can also just subtract any constant. You can see that expectation of C times grad log, which is the term that gets added, is just C times the expectation of grad log. So that term is actually 0, so it doesn't change anything. But this constant C, when you introduce it in an expectation like this, is a way of controlling variance of your estimation. And so let me move on and not linger too much here. You're going to see this under many different names. It's called the likelihood ratio method. If Doina went through the policy gradient theorem, then this technique is the basis of the policy gradient theorem. And we have many techniques for black box variational inference. And you will try and use this score function because it's so general. If you don't know f analytically, but if you can evaluate it, then you can use this gradient. So let's say your f is a physical simulator so it's a simulator of a physical system, but you can always evaluate it like an environment. Then you can use this kind of gradient. Q needs to be easy to solve because we're going to use the Monte Carlo method for this, and then Q needs to be differentiable and known. I'm going to skip the idea of amortized inference, but the idea of amortized inference is just to say that in the EM algorithm, what we were doing is we were computing phi of n over a loop for all the data points n. So this is a bit inefficient. And the idea we wanted to do was, well, can we replace the loop over n instead with a new model that if I give z will give me phi of n directly. And so that was where the idea of an inference network came into play, and sometimes called an inverse model, an encoder, or a recognition model. And you now, instead of having these variational parameters that you're optimizing for every data point, you now have a set of global parameters of the inference network. And this idea helps you spread the cost of doing inference between different data points, and which is why the word amortization is being used. So basically, when you put all of these ingredients that I put together, you basically can come up with this idea of what we call the variational autoencoder. And the variational autoencoder is an algorithm in the taxonomy of model, inference, and algorithm that I used yesterday. So it has a model, in this case, a latent variable model. It has an inference mechanism, which is based on a learning principle based on variational inference. And I create an algorithm by creating a recognition network and then doing SGD. So that combination of variational inference, latent variable models, and inference network is what we call the autoencoder. And you'll find many kinds, especially in information theory, encoder-decoder networks and stochastic versions, and they typically always implement some form of variational inference. So please, even though you're going to say all of you know about variational autoencoders, please don't go and say the VAE model. It really hurts me to hear the VAE model. VAEs are an algorithm, and the model, if you are doing generative models, the latent variable model. If you are doing classification, is the regression or classification model. So be clear about what your model is, what your inference is, and the algorithm that you are using. So that ends my first bit. There are other kinds of variational ways of deriving variational objectives. There are some limitations of variational methods. As I said, because we are approximating a true posterior with a class, they are biased in some sense, that you can never get the true posterior distribution. So in response to the question, as I said, we're trying to find methods increasingly of finding cues that become more and more general. It's very hard to design those rich families of posterior methods, so you can use many others. Optimization can be very difficult. If you're being fully Bayesian, so that you have distributions on global parameters and local parameters, and you need likelihood methods, so you need to be able to have a likelihood function, and evaluation of generative models and of variational methods or Bayesian methods is hard if you don't have another evaluation tied to a task. So these were questions of Bayesian approximation that I wanted to touch along this 3 dimensions of large sample approximations, stochastic approximations, and deterministic approximations. And increasingly, we are sort of mixing between these methods. We are combining large sample with stochastic methods and deterministic methods. So there's a lot of work for us to do there to advance this work of approximation methods. My last bit around the kind of social theory that we've been going through all the lectures for this half was for us just to think about colonialism and the fact that we are, in some sense, all affected by colonialism. If you come from a small village anywhere here in Europe, you are a beneficiary of colonialism. When the railway came to your town, the railway came because it came off the backs of money that was extracted from other places in the world. And science has been, for a large part, Bayesian theory and these kind of Bayesian approximations and computations have always been used to, in some sense, support colonial activities. And today, even though we don't have any formal colonial empires, the thinking that was established in colonial times, questions of hierarchy of race, the fact that we are all speaking today in English, the fact that what we consider knowledge, Western knowledge, is privileged over other sources of knowledge, how we treat to each other, questions of racism, sexism, patriarchy, all of these are consequences of this kind of colonial past. And, you know, statistics has for the longest time thought of itself as a moral science. And this is another trap not to fall into, to think of ourselves as a moral science, that what we are doing is moral because it is objective in some sense. Poisson models were the models that were used and actually figured out to estimate tanks in the German war. Factor analysis has been always used as some way of thinking about intelligence of individuals. And you know all about medical statistics and genetics that was used to create racialized differences between people. So it's just for us always, as we are doing our work, to consider that this history and colonial histories especially is a particular historical and contextual basis and one of those contextual values that I spoke about. And if we don't think about them, that is one of the ways that harms that are obscured because we don't question how it is we got to where we are entered. So just the point is just to be more skeptical, to be more critical, to ask a few questions. This picture on the side is a picture from 1889, I think, of Cecil Rhodes, the colonial of all of Africa from Cape to Cairo. So yeah, I want to take, there was a summary. We looked at statistical inference, latent variable models, various forms. you all gave great answers of how it is we represent distributions. We looked at Markov chain Monte Carlo, variational methods. We looked at advancing the EM algorithm to the stochastic methods, and then looked at VAEs and this question of being a bit more critical. So again, there are references for this section that are useful to look at. We won't take a 10-minute break, but we're going to just take a 2-minute break. I'm going to get some more water, give you all a bit of a breathing space, and then we're going to just take a few minutes. Okay, so let's pick up again. I'm going to share the slides again. Make sure you can all see them. Perfect. So I'm going to just do a very quick run through some more advanced methods. We weren't going to look at them in any detail because I again apologize for having come a bit later. I'll try and just take 10 minutes more. And if there are some questions, please continue to queue them in the chat. I'm happy to stay longer and answer as many questions and to probe where you think I went wrong in explaining and try to clarify things a bit better. And I've switched my camera now to a different one, so hopefully you can see me a little bit better as well. So my aims for this little section, the last section, is for you to think about the difference between inference and decision-making, because up until now we've only looked at questions of inference, to then think about topics of optimization and reinforcement, and then questions of nonparametrics and numerics. So the important difference between inference and decision-making is that inference is, in some sense, we can say what it is you can know about data. Once you're given data, you can know the posterior distribution of its generating process. You can know summary statistics, its means, other variables, and you can make predictions going in future. But decision-making is a different question. It is the question of what you can do with data. And there are very different kinds of questions. So from one, we will go from the realm of inferential methods that I spoke about for the other three parts of the lecture into the set of Bayesian decision theory. And so I don't have a section on Bayesian decision theory, but I do want to just leave you with that distinction there. And so the Bayesian methods comes again from the opening chapter of E.T. Jaynes's book on Bayesian thinking, which is that you want to build plausible reasoning systems. And to do that, we have probabilistic models. We have ways of making consistent inferences and maintaining beliefs using the methods of Bayesian computation and approximation. And then now I want to talk about how it is we can reason about potential actions and outcomes. And you know some of this already because you know about reinforcement learning and you know about causality and interventions and thinking about interventions in those ways. So a Bayesian reinforcement learning looks at the environment in this way. It splits the environment You have the external environment, which you can measure or sense in some way, and you can take actions. And internally, you may have different components. If you're doing hierarchical reinforcement learning, you'll have some options. You may have a critic if you are doing different kinds of policy gradient methods. You will have a state representation if you're doing some kind of POMDPs, and you will have a planner, whether that's Q-learning or a model-based planning system as well. So as Bayesians, of course, we want to think of things through generative processes. So an environment is for us a generative process. So we're going to place a prior on actions, and that prior then informs a probabilistic model of an environment. So this is special because an environment, the world around us, is not a place that has a likelihood. We can't evaluate the likelihood, and so we can't know it analytically, but we can observe its outcomes. We can take an action in the world. I can move my glass from here to here, and I can see the outcomes. So we have a prior over actions. I'm just writing an intermediate step, which says that you have a utility, which is the outcome of the environment with some state and action when you apply the action. And probabilistic models can always create a model by exponentiating utility functions to create probability distributions. And in this case, we want to create long-term rewards. Maybe this utility computes the long-run sum or a discounted sum, as we would do of a reward function to get that. So this is good. And in this simple framework, we can ask all the kind of inferential questions we were asking before. So the simplest question is, what is the posterior distribution over actions? And again, using everything we've done, you can maximize the probability of the log return to do this. And this is sort of many of us actually do. So one technique is, well, here's a hierarchical latent variable model. You don't know the actions, so that's a latent variable. You have a model. Let's apply variational inference. If we apply the free energy, then you'll know you'll have some expectation over a log probability. So if I do log P, I'm just going to get R minus some KL, and I'm going to introduce what I previously called Q, or that approximate posterior distribution. I'm now going to call pi so that it matches with the notation that you might be used to. And this pi, we're not going to call a posterior, we're going to call it the policy. And the policy is a way of getting actions given states and other contextual knowledge. So if you use this kind of variational method, you're going to recover many, many other methods. One thing we're going to do is use as the prior a uniform distribution over actions. We're going to assume you have continuous policy parameters. So these parameters theta are continuous, and that you can evaluate this function, the environment. You can get the reward, but you can't differentiate it. Right? And so that's the free energy. And if you combine this with exactly all these properties I just mentioned, were properties that made the score function estimator useful. So if you apply the score function gradient to this free energy, which is a variational inference for this hierarchical model, we're going to recover what we call in reinforcement learning the policy gradient method, which is basically applying the score function. What you're going to see here, and what's nice about this probabilistic approach, is that the entropy penalty, which is typically what comes up very naturally. The KL distribution between any distribution and the uniform distribution is simply the entropy. And the entropy is something that we want in exploration and in reinforcement learning, because the entropy helps us gain exploration. And you can see it's plus here. And I again added the C because, as we did in the score function gradient, the expectation under the score is 0, so I can add any C. And you always do this in reinforcement learning, which is what you'd call the baseline. And as I said, the entropy penalty is natural here, but you can now immediately find other priors on actions and change the kind of penalty and reshape the exploration mechanism that happens. If you had other knowledge of the action space, you could incorporate them into both the definition of the posterior as well as the prior. So for example, if the action had some sequences or was multidimensional and has some dependencies or has some periodicity, and all the tools of probabilistic inference are available to us. If you could differentiate R, then you could use a different kind of estimator, the pathwise estimator or the reparameterization trick. You could create different kinds of models. You can create also both stochastic and deterministic policies, so options for pi in this setting. So let's just expand that a bit more, do something slightly more advanced. Let's create a hierarchical model. There's a prior P of Z that goes into an action prior that goes into the model, and then I get the likelihood, which is an exponentiated return or reward. Because in variational or Bayesian methods, things I don't know, I need to learn posteriors for them. I will create a posterior. I will use those ideas of amortized inference to use inference networks rather than solving the EM algorithm over a loop. I will apply variational inference, so I will create a free energy or variational loss function over this thing. So again, expectation of a log likelihood minus a KL between this posterior and that prior, and a KL between this prior and that prior. And so this is pretty standard. You could just read it off now, given your experience with variational methods and Bayesian inferential thinking. And this is one way of creating a sort of hierarchical or variational MDP to do that. So there's a lot more to do around Bayesian reinforcement learning and Bayesian control. If you were to write out this as a graphical model and the kind of methods as a graphical model, then you would be able to instead use a different method of inference, which is called message passing. And when you do message passing in an MDP, you will be able to recover Bellman's equations pretty easily. It's just a different way. The message passing way that we write, where we do probabilistic inference, is just different from the way we accumulate things in Bellman's equation. So it's fun if you want to look that up. It's really amazing. In David Barber's book, he explains this really well. You can see how the EM algorithm is applicable in these kind of reinforcement learning settings, and there are many applications of EM algorithm to more older reinforcement learning methods. And there are other kind of inferential methods that are available, and we can do this in both model-based and model-free methods. I don't want to say anything about Bayesian deep learning. I think I spoke yesterday, and as well as the roundtables, that I think it's very fruitful for us to combine Bayesian methods and deep learning methods. In this distribution P of y given x, nothing about the Bayesian approach says how x is related to y. So when I wrote it out, it doesn't say the function pi, what the function pi is. So deep learning, I think, is particularly powerful because it gives us a way of saying what are good pies. If we're dealing with images, to use convolutions. If we're dealing with sequences, to use attentional models or self-attention of some form, or recurrent models. And again, here is when you need to be very pragmatic as a Bayesian. You don't want to be Bayesian and put a posterior over every parameter. That could be 1 million or 1 billion parameters. That would be very hard to do. So we can be selective and clever about which things that we put priors and posteriors on. Bayesian methods for very deep networks is still very difficult, but there's lots of work on variational inference in these settings. Monte Carlo dropout, variational dropout. Sampling from multimodal posteriors is one of the interesting questions which comes up. And you have lots of now theoretical analysis using this work of tangent kernels and neural tangent kernels to understand what happens if you take infinite width models in this settings and how they relate to other kinds of Bayesian methods like Gaussian processes. And you have also new MCMC methods being developed by thinking through this Bayesian deep learning approaches. One of the recent ones is called cyclical stochastic gradient MCMC. Bayesian optimization is a third class of things in this optimization and reinforcement, where we can use Bayesian methods to optimize a global function that won't be known to us. And again, the function may be something we can evaluate. So a Bayesian approach is, again, the same as every Bayesian approach. We don't know the function, so let's put a prior over this unknown function. And so we're going to need methods that are priors over functions. And one prior over function is called a Gaussian process, which I'm just writing in GPs. I won't explain it in more detail. Of course, if we put a prior, what we're interested in is getting a posterior of that function given some data. And what is interesting about Gaussian processes is that they are closed. So the prior and the posterior remain in the same form. So it's very much like that very simple method that seemed very useless in practice of conjugate methods. But when we have these kind of stochastic processes, they are infinite dimensional. They look in many cases like conjugate method. And that's why we want to study those conjugate methods, because they give us this insight of how to manipulate these infinite dimensional objects. And then basically we're going to use this posterior and the uncertainty to drive the searching method to help find the maximum value of this function. And so what you will do is introduce an acquisition function, and the typical one that's used is to take the mean plus some scale of the variance. And so to get this mean and variance means that you want to be Bayesian, because Bayesian methods give you very good ways of estimating variances and means. You can try other methods here like randomized forest as well. And this is a recursive approach to updating. I want to just make that connection. Since we've now introduced GPs, there's very deep dualities probabilistically between many methods that we see, which show us that they're actually very much the same kinds of methods. So basis function regression is the basis of deep learning, where the basis functions are recursive compositions of linear functions. If you were to take this basis function regression and do an optimization where you transform from a set of primal variables to a set of dual variables, where the primal variables are these phi's, and you move to a set of dual variables, you'll be able to use the kernel trick. And conveniently, while you were waiting for me to join, you use the kernel trick to derive some of these methods, and you know how to manipulate the kernel trick, and you basically get this function, which is common to every kind of kernel machine and kernel method. And if you were to be Bayesian about these kernel methods, you would then naturally get to the point of getting these GPs, because these primal methods are just the mean, correspond exactly to the mean of these GPs. So you get this kind of changes that you can do from deep networks. If you took an infinite limit, you could get to a Gaussian process. If you took dual functions, you could derive the kernel machines. If you went from kernel machines and you wanted to treat them in a Bayesian way, so not have this regularizer, but have a prior instead, you'd recover Gaussian process. So there's something very deep. Many of the methods that we study aren't fundamentally very different. And you see how they are different when we apply the inference procedure, and then we derive ultimately the kind of algorithm that we use. So Gaussian processes then come up as one. They are priors over functions. And what's special about them is that they are adapting to the number of data points. And so they are neat, computationally challenging, but very worthwhile a study. Gaussian processes are one example of Bayesian nonparametric methods. Nonparametric methods, I want you to think about a difference between fixed dimension models, which are models that I describe for the most part, deep networks, latent variable models, etc., versus adaptive dimension models, which are models like Gaussian processes. So the difference is that in one case, maybe that's basis function regression. Gaussian process regression is an example of an adaptive dimension model. And so fixed dimension models, as they say, have a finite number of parameters. You fix this up front when you design the model. But adaptive dimension models have an a priori infinite number of parameters. And when you are given a data set, you instantiate a finite number of parameters that corresponds to that data set. So Bayesian non-parametric models have a complexity that grows with the data set. So as you introduce a new data point, the size of the model, the number of parameters are increasing. In another sense, you could think of Bayesian non-parametric models as treating the data as parameters themselves, and then you are interpolating the data points in clever ways. But they are very flexible model, really neat. They are very robust to overfitting. And again, we come to this point of Bayesian non-parametric models by going back to the very first slide that I showed around De Finetti's theorem. When I introduced De Finetti's theorem, I said De Finetti's theorem says that there is a prior distribution with a parameter theta. But it didn't say what the dimension of that theta is. And when I began explaining Bayes' rule, I said, let's assume it has a density and that there is a finite dimension. But if we wanted to, we can now, using De Finetti's theorem, have the theoretical tools to analyze and understand infinite dimensional models. And instead of using a density, like Pierre mentioned in the questions earlier, you would instead use the measure theoretic properties. You would then introduce the radon-Nikodym derivatives, and then you would do the models and manipulate these probabilities of infinite dimensions using that set of tools instead. So a mixture model is the one that comes up most often in this case. I don't know if you saw mixture models. I did try to look through some of the slides. I don't think they appeared anywhere, so I thought it was worthwhile us looking through them. In a mixture model, you would typically try to set a set of cluster parameters. Let's say you have k clusters, and you're going to just set some parameters phi k for all k of them. You're also going to have some categories. So if you have k categories, you're going to sample from a Dirichlet distribution, which is going to give you the probability of sampling from any of those pi categories. Typically, what you want to do is then I need to choose an index. So I'm going to choose an index z, which is going to say, given these probabilities, I'm going to choose index I. And then I'll pick up those particular sets of parameters, and then you're going to get the parameters theta n by indexing from the set of phi at the index that you chose, and then you generate the data. So this is typically how you would write out a mixture model. It's a very standard view. It's the one in all the textbooks. It's the one we introduce when we are in classes and introductory classes on machine learning, learning about mixture models. Another view is to use what is called the random measure view. It's pretty much the same. It's identical. It just writes things slightly differently. Again, you will start by generating the set of K clusters. There will be a set of categories that you want to generate pi, which gives the distribution over parameters. And what you're going to do, and this is where the writing is different, we're going to, instead of representing this sampling from an index and then choosing the distribution, we're going to combine it in one by writing out a discrete mixture. So it is the sum over K categories with parameters phi and a delta distribution. And when you sample from this distribution, you're going to get the probability pi at the phi kth index. So this is just a notational rewriting, and then you sample from the mixture from this distribution G, and then you sample the data. But the reason we want to write it out in this random measure view is that it is now the right kind of mechanism and notation for us to ask a question, what happens when we make K become infinite? And as I said, we want to create this kind of adaptive dimensional model. So this random measure view is exactly the same in the finite dimension. When it becomes infinite, we're going to rewrite it in this way. We're going to do this integration, which says it's P of y given some theta against some measure d of g of theta, and this measure is represented through this kind of discrete probability, which is going to have this infinite dimensions, and conveniently the stochastic process which corresponds to such kinds of measures are Dirichlet processes, and Dirichlet processes then have exactly this kind of graphical model that we have. And there are many ways to represent this and to sample them using stick-breaking processes, Chinese restaurants, which you may have heard, the kind of urn scheme that I used to talk about exchangeable processes in the beginning is what comes again. And again, like the Gaussian process and like those conjugate models, the Dirichlet process has that nice property that its posteriors are also Dirichlet processes. So we can manipulate them very easily. And you get this idea of taking infinite limits, looking at models that adapt to the number of data in many ways. As I said, for Bayesian linear regression, you have Gaussian processes. For latent variable models, you can generate something called Indian buffet processes. For time series models, we'll get other kind of temporal processes. And there's a lot of interesting work to do here. So I think we have enough now to just look at the spectrum of kinds of models of various dimensions that we think about when we are building Bayesian machine learning. We are thinking about dimensions of whether our models are discrete or continuous, especially if they are latent variables. We are thinking about whether they are deep models or they are linear models. And we are thinking about whether they are parametric models or finite dimensional models versus non-parametric or infinite dimensional models. And you basically get a cube, and from that cube, you can see that we have explored almost every kind of model. If you want to build a deep non-parametric model with continuous latent variables, you can get deep Gaussian processes, GP state space models. If you want to build a linear parametric models with continuous values, PCA, factor analysis, latent Gaussian field models, Gaussian linear dynamical systems. There's a lot of fun models that we have explored and then have different applicabilities and use cases. The final one that I wanted to look at is this idea of Bayesian numerics, where we want to now think of numerical methods not just as numerical discrete things that we apply an optimization to, but we want to think of them themselves fundamentally as learning algorithms, and particularly as Bayesian learning algorithms. So again, this will allow us to say that computation is something that is uncertain, and this is the case because, like I explained when we were doing Monte Carlo, when we are doing stochastic gradient descent, Monte Carlo evaluation, we are generating random variables that have uncertainty. And then we can use that to study many different kinds of computational bottlenecks that we have. Methods of optimization, sampling, integration, solving ODEs, linear algebra methods, line searches. And so one of the classical papers, other than the paper that I showed you earlier on Monte Carlo is fundamentally unsound, is this paper by Percy Diaconis called Bayesian Numerical Analysis, and it will do exactly that. Again, by Philip Hennig in the Tübingen group, has done amazing work to expand in this space of Bayesian methods, whether they are at inference time, where we are doing quadrature and integration, whether we are doing it at prediction time, when we are computing posterior predictive distributions, whether we are doing it at action and decision-making time by computing posteriors over action, and when we are doing it estimation time by doing optimization. And they've done amazing work on Bayesian quadrature, looking at conjugate gradients as Bayesian methods, looking at Bayesian approaches to line searches and ODEs and PDEs. So there's a lot of fun methods here to look at. I'll just end then by talking about contextual values, the thing I began at the very beginning. This is one of the pictures, probably one of the most famous pictures we have in all of history. It is the picture of the Nuremberg trials. It is the trial at the end of World War II, where the Nazis were asked to be held to account for the atrocities that they did across all of humanity. The trial of Eichmann, for example. And one of the most important things and the outcomes of the Nuremberg trials are called the Nuremberg Code. Because at the end of World War II, the relationship between the public and we as scientists was fundamentally broken. Science was used to create the gas chamber, to create the atomic bomb, to kill, maim in every way you could imagine. So the Nuremberg Code set forward 10 fundamental values that we need to now put forward to create research, especially for scientists. The voluntary consent must yield useful results, must justify performance, must not create injury, physical or mental, and there are many others. But, you know, as much as we have the Nuremberg Code, these kinds of injustices, harms, and unethical values continue to happen. And one of the most famous cases comes from what is called the United States Department of Health public study of syphilis in Tuskegee. And what they did was they had a case study of 400 Black men, African-American men, who were purposefully infected with syphilis to understand the progression of syphilis in the human body. And this was one of the longest longitudinal studies we have in history. It went on for several decades. And the worst part of this kind of study is that even after the cure for syphilis was found for several decades, these people were still continuing to be infected with syphilis. And so the outcome of the discussion and the discovery of this kind of really horrendous treatment, something so horrendous, was called the Belmont Report. And the Belmont Report now today forms one of the bases of our ethical and contextual values. And the Belmont Report put forward 3 principal values for us all to think about in our research. The first one is respect for persons, which means that every person must be given autonomy and individuality in that basis. That we need to do research that is of beneficence, that our research must be designed to, at one end, maximize societal benefit, but at the other hand, minimize harm to individuals. And then there's the point of justice, that justice research must be distributed across society. It must not be, as we have today, and as in both of these cases, those people at the edges of society, those people who are minorities, who are in racial groups, who are the poor, are the ones who take the risks of scientific advances, technological advances. And today there's a lot of discussion around these kind of ethical values, and for spaces like machine learning and AI, there are typically 2 others that people suggest we think about. One of them is called non-malfeasance, which is do no harm, which is used in medicine. And the final one, which is called explicability, which is around explanation and transparency. So that basically ends it for me. As I said, at the very beginning of these 2 lectures, I wanted us to talk about a definition of probability as a measure of belief in a proposition given evidence. And evidence became very important for us to weigh. And then I began by motivating fundamentally Bayesian methods using De Finetti's theorem, which explains why we have parameters, why we have priors, why we have posteriors, and how we should think about marginalized likelihood. And there were several kinds of concepts: the question of integration, the question of model, inference, and algorithm, that Bayesian statistics puts priors over all quantities, and we want to compute all quantities as distributions, so we only have the problem of inference. We looked at deep models. conjugate models, models over environments and hierarchical models, and inferential methods like Markov chain Monte Carlo, variational methods, the deep kind of dualities we have between various methods, and how that unpacks for us when we think of the space of different consideration, broad spaces of models. And ultimately, I did want us to do a touching on important questions of ethics and social impact, whether those were epistemic and contextual values, to think about the role of colonialism and how it is shaping our thinking even today, and to talk about simple topics of neutrality, decolonization, and ethical value criteria. So decolonize, be critical, and thank you, everyone. I have again some papers in this section. I have several book recommendations for you all if you wanted to pick up some more. These books are the classical books that have many different kinds of topics. The Bayesian reasoning book, I will say, go and read the chapter on MDPs and where Bellman's equation is derived. It's really, I think, the only book I've seen that. And Kevin Murphy's book will give you the exercises to do everything we have done over 35 chapters. So it's pretty comprehensive. These are some books I have found that have always shaped my own thinking. E.T. Jane's book is my favorite of them. I asked everyone to read the first 2 chapters of that book. And then you have other more advanced books, Monte Carlo Statistical Methods. You can read this one cover to cover, maybe over several years, but it's a pretty good one. Bayesian Filtering and Smoothing. So much thinking have come from Simo and this group. And this is a classical book about graphical models, exponential families, if you want to study a bit more. And then around these ethical values, there are 3 books which maybe are interesting. One of them is more a philosophy of science book, which is called The Taming of Chance. And this is a question around the history of statistics and how statistics became and chance became put into a field of statistics and the kind of impact that it has. These kind of contextual values and how we as computer scientists can become embedded and co-opted into some of the world's most evil of activities is described in this book, IBM and the Holocaust, which I think is pretty good. If you want a piece of literature to think about colonization, this book is just 100 pages by Jamaica Kincaid. It's called A Small Place, around the history of Antigua and how colonialism shaped their thinking and self-confidence and self-hate that comes into a people, and how you have different racial relations. So I think it's pretty fun one to do. I thought maybe I'd end, since it's the last one, for us to read a poem together. It's a poem that I use very often to think about my own work. So it goes like this. It says, "Dearest, note how these 2 are alike. This harpsichord pavan by Purcell, and the race's 12-speed bike. The machinery of grace is always simple. This chrome trapezoid, one wheel connected to another of concentric gears, which Ptolemy dreamt of and Schwinn perfected, is gone. The cyclist, not the cycle, steers. And in the playing, Purcell's chords are played away. So this talk or touch, if I were there, should work its effortless gadgetry of love, like Dante's heaven, and melt into the air. If it does, of course, I have fallen. So much is chance, so much agility, desire, and feverish care, as bicyclists and harpsichordists prove, who only by moving can balance, only by balancing move." And I want you just to remember those last 2 lines, who only by moving can balance and only by balancing move, is the way I think we should approach machine learning, in balance and in considering the kind of changes and impacts we actually want to have. So again, thank you. I apologize for being late in the second half. It has been amazing to meet you all. Thank you for the wonderful discussion over the roundtables. And please reach out if ever I can help with anything you need in future to have more discussions on Bayesian learning. And I look forward to reading all of your papers in future and as to how you will advance this field of machine learning, and to cite your papers and to work with you and collaborate with you. So thank you very much.
Thanks, Shakir.
Thank you very much. It was.
We have very little time left, unfortunately, because we have final remarks planned in 7 minutes. So maybe let's maybe 2-3 questions. Can you give us 5 minutes, basically, so we can start the next session?
Yeah, so I think Sophia wanted to ask a question. I already promoted her to panelist. So Sophia, feel free to go ahead.
Hi, Sophia.
Hi, thank you so much again for the amazing lecture. So I have a very kind of technical and practical question that I can ask quickly and you can basically ignore about reducing the variance of the score function estimator with discrete latent variables. Yeah.
Okay, great. Yeah, so I think discrete variables are actually a much more difficult kind of monster to tackle because discrete variables don't have the kind of tricks that I showed you. The tricks of identity trick, the trick of doing log probabilities that apply only in continuous spaces, the tricks of changing the nature of the integral into a discrete sum, none of those things apply. So typically you have seen the trend that people do is to smooth out those functions and then do the kind of continuous estimation in the function. So I think what we need to do, if you want to do discrete spaces, you are going to have to use much more knowledge of the discrete space that you are in. So if you know that your function, for example, is submodular, then actually you can do a lot of stuff because then you don't need to enumerate over the whole discrete space. You can just turn it into a convex function and it's going to work. So I think that's sort of one direction of where a lot of prior knowledge, much more prior knowledge is going to be introduced. And actually discrete methods, learning with discrete variables is one of those sort of holy grails of machine learning. It's a problem everyone wants to keep going back to because it is so difficult to do. Don't know if there was another one.
Yeah, I think we have time for one last question. So Pierre, Cyril, you had a question. I already promoted you as well. So feel free to go ahead.
Hi, Pierre.
Okay, Pierre, are you there?
Yeah, I'm just a problem with rigs. Sorry, it's just after poetry, it feels strange, but originally variational methods were a way to turn PDE problems into practical optimization problems. So I was wondering if there were deep connections with the fact that you can use variational inference with, is there some underlying structures, some notion of solution space, for instance?
Yeah, so again, the variational methods came to us from a lot of work in statistical physics. And actually now I think of a really good book in statistical physics that it's really amazing that even the first 2 chapters of this book, I'll try and put it in the channel or something. So yeah, there are sort of many deep questions there. In the PDE space, you actually know a little bit more about the solutions because you have kind of structures of the homogeneous equations or inhomogeneous equations, and you also know a little bit about the initial conditions. So there's been a lot of work in this space. I won't say a lot more about it, but I think you can do, and you see a lot of work right now around doing exactly what you're saying, reversing the space to say that we can represent probabilities through this kind of sampling process, using PDEs to represent the space of probabilities, and then evolve the kind of distributions to get richer distributions that then make those kind of variational approaches a little bit more richer. So yesterday, someone asked, I think, on the round table, if, Georgia said in the kind of little interview we were doing for those videos, if there was one thing I wish I could learn but still have not doing, and it's exactly this question. There's a book that I want to read for the last 2 years. It's my New Year's resolution on machine learning and stochastic differential equations. So I'm hoping this year I will get to it, but yeah. So I think that's our last question. Again, thank you all. I hope you had a wonderful machine learning summer school. Even though we weren't physically together, it has been really amazing for me. Thank you for giving me your energy and teaching me what you think about. And I hope we'll get to meet in person soon.
Thank you.
Thank you very much, Akir. It was, I think, the best way to finish this MLSS. Yeah.
All right. See you soon in the final remarks.
This is the end of the lectures, and see you in the final remarks soonish.
Ciao.
Bye. Okay. So I stopped the recording.
Yes, stop the live stream as well.
Yep.